For deconvolution, one uh, thing that we saw, that is inverse system. Okay. What do you mean by inverse system? That if you know the transfer function Az, okay, then if you just inverse it, then it will become inverse transfer function, and it is the transfer function is the system, okay, inverse of the original system. So Az, let us say Az is your FIR system. So FIR system is what? FIR system, I have written that output depends on only on present and past values of inputs. Okay. So like a moving average filter, moving average filter. So HN is a finite impulse response, then it is valid for certain finite number of sequence, okay, and outside that, that is zero. So generally it takes this form. The transfer function of that system takes this type of form: 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3. Okay. And it comes from, you know that um, yn is equal to xn plus xn minus 1 plus xn minus 2. That means present and past values of input. So if you take the z transform of that kind of expression, okay, that is, it will become yz, and it is equal to x of z into 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3. That is a expression. So if you calculate then yz by xz, then it will become 1 plus z inverse plus z to the power minus 2 plus z to the power minus 3. So this expression is has actually only zeros. Okay. That means only numerator is there, no denominator, only numerator in the transfer function. So if only numerator is there, that means there is no poles, only zeros. So that represents actually FIR system. Okay, FIR system actually has that property that it has only zeros, no poles. Okay, and its example is moving average filter. And for IIR system, both numerator and denominator are present. Okay. Can anybody tell why both numerator and denominator would be present in IIR system? Can anybody tell? This means only zeros will be there. Both the zeros and poles should be there in case of IIR. Okay. This is because the output depends also on past values of output. Okay. Then there are terms comes like yn minus 1, yn minus 2, yn minus 3, like that. So for that, again, yz into 1 plus z inverse plus z to the power minus 2, z to the power minus 3, those type of terms will be there. So you will get yz by xz, that is equal to expression, some expression numerator by some expression denominator. So that actually represent IIR system. Okay, so that is different thing. I am recalling, and I will also recall always whenever some issues appears, okay, some topics appears like that, where you will use FIR, where you will use IIR. So I am recalling that only. So here in this case, we take AZ, say it is a all zero system, and zeros are located at R1, R2, R3, like that. Okay. So if you take the inverse of it, then it will become uh, inverse, and it will have 1 by of that 1 plus z inverse plus z to the power minus z to the power minus 3. So it will become consisting of only poles. Okay, so whereas in case of FIR we had zeros, now it all zero system. Now if we take the inverse, it will become all pole system. Okay, so that is the inverse system, example of inverse system. Okay. Now we take another example. Okay, Hn is equal to 1 by 2 to the power n of un. Okay. Now, what is the now determine the inverse of the system? Okay. Inverse of the system will be what? Inverse of the system is Hz. Will be one, then Hz. First you calculate Hz, then you calculate 1 by Hz. So Hz is this one. You take the this thing. Okay, up to the power n un. Actually, its Fourier Z transform is it resembles to a to the power n un. Okay, a to the power n un. So it will be 1 by 1 minus az inverse. Okay. So in place of a, we write half. So 1 by 1 minus half z inverse. And since it is a causal sequence, okay, so its ROC would be outside or exterior of a unit of a circle of radius a. So a is half, so its ROC would be mod z greater than half the exterior of a circle, since it is a so it is a causal sequence. So we get this this thing. And also now what is the inverse of it? Inverse of it is now 1, since it is 1 by, so it is only 1 minus half z inverse. Okay, 1 minus half z inverse. So it's now if you take the in time domain, what is the impulse response? In time domain, impulse response is inverse. Take the inverse Z transform. So inverse Z transform of 1 is delta n. Okay, and Z inverse is half delta n minus 1. Okay, because impulse response is what? If you give the input impulse, okay, input is impulse. So it is what? Hij means yn by yz by xz. So yz is equal to 1 minus half z inverse into xz. Now you take inverse of that. So y1z means y1n. Okay, yin is nothing but hin, because we have applied xn as delta n. So hin, y of in is hin, and in place of xn is delta n is there. So delta n into z inverse means delta n minus 1. So it becomes delta n minus half delta n minus 1. Okay. So this is one example to calculate the inverse of a system. Okay. So why inverse is required, that I explained in the last class, that suppose if you take convolution yn is equal to x of xn convolution hn. Okay. Then if you want to know input, okay, xn, provided you know provided you know the hn and xn, yn, output and impulse response, if you know, then if it is, then it is inverse of that hn or yn convolution 1 by hn. So 1 by hn is the inverse of the system. Inverse system, inverse of system having impulse response hn. Okay. Yes. So this is one example. Now, what do you mean by deconvolution. Okay. So it is written that from the output sequence, if you wish to determine the impulse response of the unknown system. So suppose you know, if you know the input that is applied and you know the output that is you are getting, we know that means xn and yn. So what will be the transfer function hn for that case? So that is actually called system identifications or identify the system. What is system? System means system is always characterized with transfer function. So what to identify the transfer function or to identify the HN impulse response, okay, of the system. So HN can be calculated, okay, by different way. So we see that mm, if you know the ratio yz by xz, okay, then you can calculate hz. Okay, so that is called deconvolution or to so why deconvolution means deconvolution is used to identify one unknown system or to determine the transfer function of a system whose inputs and outputs are known. That is called deconvolution. It is used to identify one system whose inputs and outputs are known. Okay? So we start with this relation yn is equal to hn convolution xn. The formula tells that it is actually summation aks minus infinity hk x of n minus k. Okay. So in z domain, what is the relation? That is product of these two. Okay, yz is equal to hz xz. Now we get the relation y hz is equal to yz by xz. Okay, yz by xz. So uh, xz and yz are the z transform of xn and yn. Okay. So if you individually know the expression of yz and xz, then find the ratio of that and apply partial fraction. You'll get hz. You will get hn. Okay. So there is one example, okay, of deconvolution that uh, deconvolution is what that uh, suppose yn is given in terms of this yn is equal to 1 for n is equal to 0, n is equal to 1 is 7 by 10 and 0 otherwise, and xn is given by this relation xn. We have when xn is given this, that n is equal to 0 it is 1 and n is equal to 1 it is minus 7 by 10, and at n is equal to 2 it is 1 by 10 and 0 outside, then this is the output yn we get. Okay, so question is determine its impulse response and input output equation. Okay, so first what we do, we write yz. Okay, yz how will be able to write by uh, by assuming that there are different these values at different locations of time. So yz is 1 plus 7 by 10 z inverse. Okay. And first it is how it is done. So first you take the z transform. Okay, z transform is what? It is summation n is equal to minus infinity to infinity. Okay, x of n z to the power minus n, x of n z to the power minus n, or summation y of n into z to the power minus n. Now at different time of n, we know the values, so we know why n exists at n is equal to 0, at n is equal to minus 1, n is equal to 1. Okay, you see, so that time it will become 1 plus 7 by 10 z inverse. Similarly, xz is calculated with the z transform of xn. Okay, 1 minus 7 by 10 z inverse plus 1 by 10 z to the power minus 2. Okay, so uh, we get this one. Now we factorize it. We take multiply into two terms. Okay, and we see that this is the expression of hz. Okay, now you can easily calculate, and this is done to calculate to represent in terms of partial fraction. Okay, partial fraction. So for this you can get individually and calculate the inverse of z transform. Okay, the last expression is your inverse z transform by partial after of expressing in partial fraction. Okay, and this expression yn, okay, how it is obtained? This expression yn, now this is obtained by from the previous equation, from multiplying this yz into 1 minus 7 by 10 z inverse plus 1 by 10 z to the power minus 2. Okay, that is equal to xz into 1 plus 7 by 10 z inverse. Okay. So now you just apply the inverse z transform. Okay, then it will become y of n, and z inverse represent yn minus 1, z to the power minus 2 represent yn minus 2. Similarly, xn and z to the power minus 1 with xz represent xn minus 1. So you take add all this term one side and output terms in the left side, other side. Okay, that is yn. You will get the function yn. Okay, so this is the way how to calculate the deconvolution. So is it clear, this method that I described?
Yes.
If you make a mistake, okay, fine. So next we go another topic. Okay, that is probably the last topic in the first module, although it is a very big topic. Okay, but we will try to not go very detailed. Okay, and because lot many applications are involved, you can go to the slides that I have uploaded for this PPT, and also after that I have changed some slides, so I will also upload the new one. Okay, but if you go through it, you will see the different types of filters are there at the end of this PPT. So I will not get time to describe all, but I will touch or I will give the basics, okay, of to design the filter, okay, to design or to understand the filter behavior. Okay, and that comes from the realization of discrete time LTI system. Okay. So what is the role of filter? Filter actually shapes the spectrum. Okay. Filter shapes the spectrum of any system. Okay. So it is called spectral shaping, or if we particularly customize want to customize the filter's frequency spectrum or frequency response, if you want to customize the frequency response, then it is called frequency selective filtering. Okay. That means at some selected frequencies, at some selected frequencies, we have some characteristics like they may have high gain and they may have low gain, okay, or zero. They may have gain or they may not have gain, okay, like that. So it is called frequency selective filtering. Okay. Now I am not telling what is written there, that there are a lot many applications, okay, of this, like for commercial communication channel, okay, then radar, sonar, communications, and there are different analysis of signals. So what are the ideal characteristics of filter is that there are two region. Okay, one is called pass band, okay, and another is called stop band. So in pass band, gain is high, and in stop band, gain is low or zero. Okay. Stop band gain will be totally zero, and in pass band gain is high. And another characteristics is linear phase response. Okay. So linear phase means the phase of the frequency component would change linearly. Okay. Whatever the frequency components are present in a given signal, in a signal that is applied to a filter, all the frequency components must undergo different phase shift. That is the linear phase characteristics. Okay. So there is very important in case of filter, that is phase characteristics should be linear. Now next in diagram we see that how what are the shapes of different filters. You can see first one is called low pass. Okay, low pass, okay, it is high gain near near at zero frequencies or low frequencies, and up to cutoff frequency omega c it has high gain, that is gain 1. So it tells the bandwidth b, okay, and you see the frequency goes from minus pi to plus pi, as because it is a digital frequency. Okay, in discrete domain we use this frequency. Okay, so it is 0 to pi, and high pass filter is actually up to at the high frequency pi. After the frequency cutoff frequency omega c it has gain. Okay, and band pass it is in between some range, it is gain high. Okay, then band is band pass. Okay, and band stop is what, it is all over the frequency range, it is high except certain range, except certain band it is gain 0. And all pass means for all frequency it is as high gain. Okay, this is the ideal filter characteristics. But practical filter differs much uh, uh, from the ideal characteristics, differ much from the ideal characteristics. So then another that thing is a linear phase. Okay, linear phase is what? It is actually phase varies linearly the with frequencies. Okay, so otherwise the signal would not be constructed properly. Okay, low frequency component will fall into high frequency component, high frequency component will fall into low frequency component. So that kind of unknown behavior, unknown phenomena we'll see. So let us define that the transfer function h omega is c into e to the power minus j omega n 0. Okay, this is one characteristic frequency response. Okay, and within certain range have these characteristics. Okay, now if you apply uh, if you calculate the y omega is what x omega into h of omega, x omega into h of omega. Okay, so if you apply if you put the values of h omega, okay, you will get it c into x omega into e to the power minus j omega n 0. Now if you take the inverse of it, this time Fourier transform, inverse Fourier transform, it will give you yn is equal to, since in frequency domain x of omega is multiplied with e to the power minus j omega n 0. So in time domain, it would be time shift. Okay. So it is c into x of n minus n 0. Okay. So this is actually delay of certain amount. Okay. Output is actually nothing but a delayed version of the input. Okay. Delayed version of the input. And how much is the delay? Delay is the n0. Okay. N0 is the amount of delay. Okay. Now, what does we infer from this? We infer that the filter output simply a delayed and amplitude scale version of the input signal. If you pass the input signal x into such kind of filter where transfer function is c into e to the power minus j omega n 0, so input signals undergo through a delay and scaling, scaling by some value. So so filter does what? Filter performs some delay, okay, of the input signal. So what is the phase characteristics of this? That phase theta omega is here in this case e to the power j theta, that is theta part is minus omega n 0. Okay. So this is actually, if you plot this is the phase, it is a linear y is equal to mx characteristics where m is constant n0. Okay. There is a linear characteristics. Okay. So this phase is linear. Now if you take this another factor another term that is called a parameter that is called group delay. Okay. Change of phase with respect to change in frequency. Change of phase with respect to change in frequency. That is called group delay. There are many waves, many frequencies. All the frequencies are called a group. Okay, it's a group of frequencies. So each individual frequencies undergo different delay, slightly different delay. So what is the overall delay? It is called group delay of the filter. So it is d theta d omega. Okay. So if theta omega is constant, that is phase is constant for all the frequencies, okay, that it does not depend on frequency, then group delay will be 0. Okay. So same time delay. So it is and if it is you see that if it is a linear, if theta omega is linear, so if you take the differentiation of that, then it will get constant delay for all the frequencies d theta d omega. Theta omega is linear, so it is n0. Okay. If you see it is n0 delay, so it is constant. So, uh, so uh, group delay is constant. So in that case, all frequency component of the input signal undergo the same time delay. So if it is if phase characteristics is linear, then all will go undergo the same time delay. So this property you must have studied in other system also. So now next important thing is that uh, poles and zeros. Poles and zeros for filters. Poles and zeros for filters. What role they play? Poles and zeros. Filter, what role they play? Okay. So, uh, so you can see it is written that the basic principle underlying the pole zero placement method is to locate poles near points of the unit circle corresponding to the frequencies to be emphasized and to place zeros near the frequencies to be de-emphasized. Okay? So that means what? That the frequencies, okay, at which we want to have gain, the frequencies at which we want to have gain, that is omega, at which we want to have gain, those frequencies should be placed at poles. Poles make a transfer function or any functions I. Okay, this is numerator by denominator. Denominator corresponds to poles. Numerator corresponds to zeros. If denominator is zero, that means system function is high. That means if poles makes the functions or system functions high and zeros make the system functions zero. So just you need to place the frequencies, okay, at corresponding poles. If you want to have high gain to those frequencies, you need to place the frequencies to zeros. If you want to get the gain low at those frequencies. So that is the concept. So now from the values of Z, Z is what? Z is equal to R into e to the power j omega. Z is equal to R into e to the power j omega. So if you know the omega, okay, that is any frequency, then you can calculate the value of Z. Okay, then those Z will be used for either poles or zeros. Poles for making gain high, zeros for making gain low. Okay? This is the basic concept. Next slide we will see it. Will be much more easy to understand. Another concept is all poles should be placed inside the unit circle in order for the filter to be stable. Okay, that we have earlier studied that this alpha e to the power n, this alpha is less than 1. Okay, that means or alpha to the power n un or a to the power n un, whatever it is. If it is less than 1, that means system vivo stable. Okay, did not increase. The system gain will not be infinite, it will be stable. Similarly, complex conjugate, all the complex zero and poles must occur in complex conjugate in order for the filter coefficients to be real. Yes. So then only filter coefficients should be real. You have seen that if the poles are complex conjugate, then coefficients are also complex conjugate. So then when you will get the product, then this coefficients will be real. It will not be complex. Okay. So then next it is uh, next one important slide. So you see that here just only it is shown that how a transfer function is has the zeros and poles. Okay, Az is your transfer function, and Az is your transfer function, and it is consisting of uh, uh, expression at numerator and denominator. Okay, and numerator it consists of zeros at positions zk. Okay, and there are m number of zeros. Okay, m number of zeros, k is equal to 1 to m, so it is 1 minus z1 z inverse into 1 minus z2 z inverse. So there are m number of zeros, and there are n number of poles in the system, 1 minus p1 z inverse into 1 minus p2 z inverse, like that. So this next part is not required. So here you have got to know that the transfer function consists of zeros and poles. Okay. Now, some general rules I'll describe here. That let us consider one low pass filter. Okay. Low pass filter. In low pass filter, what is the characteristics? Is that near zero frequency it has high gain. That means near low frequency it has high gain, and at high frequency, that is digital frequency pi, it is zero gain. Okay, so in that case we should have poles, okay, exist at low frequencies. Okay, because poles makes the function high, filter function or system function high. Similarly, zeros should exist at high frequencies, because high frequency we want to have low gain. So zeros should be there at high frequencies. It makes the function zero. Similarly, for high pass filter, here you see the characteristics for high pass filter, that high frequency, a pi near to pi region. So uh, it is what it is, gain is high. So poles should be placed. Poles should be placed. Okay, poles should exist at high frequencies. Okay. Poles is actually what? Poles or zero is actually what? It is a frequency point or jet points. The points in a jet plane. So those values of z will be, you have to set according to your filter, desired filter. Okay. So z is what? Z value is r is equal to e to the power j omega. Okay. So now see that if omega tends to zero, okay, omega tends to zero means what? Then z tends to 1. Okay. If omega tends to 0, that means z tends to 1. Okay. So that means low frequency, that means it corresponds to low frequency points. Okay. Low frequency points. Low frequency points represents z tends to 1. Okay. Near to the unit circle. Plus 1. Z tends to plus 1. Near to the unit circle. Okay. And omega tends to pi, means high frequency. And for this, z tends to, z is equal to how much? Is e to the power j pi. E to the power j pi means it is minus 1. Okay. -1j actually to the power r into cos omega. No, r into cos pi. Cos pi means cos pi का वैल्यू कितना है? cos pi का वैल्यू anybody please? What is
-1.
it? -1. Yes. So cos pi अगर -1 है तो z का वैल्यू होगा -1 provided r is equal to 1 यूनिट सर्कल. Okay. So cos अगर ओमेगा 0 है तो cos 0 1 होगा और cos पाई है तो -1 होगा z का वैल्यू. तो ये पॉइंट्स मतलब हाई फ्रीक्वेंसी में z का वैल्यू -1 होता है. ओके. और लो फ्रीक्वेंसी में z का वैल्यू 1 होता है. दिस थिंग यू हैव टू कीप इन माइंड. नाउ फॉर लो पास फिल्टर, लो पास फिल्टर में क्या चाहिए हमको? हाई गेन चाहिए लो फ्रीक्वेंसी में. ठीक है. तो लो फ्रीक्वेंसी में हाई गेन चाहिए तो लो फ्रीक्वेंसी मतलब ओमेगा 0 और ओमेगा अगर 0 होता है तो जेट का वैल्यू 1 है. तो अभी तुमको चूज करना है कि इसको पोल बनाना है कि 0 बनाना है. कोई बता सकते हो? लो पास फिल्टर में जेट का वैल्यू 1 है क्योंकि फ्रीक्वेंसी ओमेगा 0 है. तो ओमेगा 0 है और लो फ्रीक्वेंसी में गेन हाई होना चाहिए. लो फ्रीक्वेंसी कॉरेस्पॉन्ड कर रहा है जेड इज इक्वल टू 1. सो ये जो जेड इज इक्वल टू 1 है तो इसको पोल बनाना है कि 0 बनाना है लो पास फिल्टर के लिए? कोई बता सकते हो?
सर पोल.
Yes. Who told Paul?
सर हर्षवर्धन अग्रवाल.
Harshvardhan. Fine. So that means so लो पास फिल्टर के लिए पोल का वैल्यू होगा नियर अबाउट 1 टेंस टू 1. ठीक है. और 0 का वैल्यू होगा नियर अबाउट -1 क्योंकि हाई फ्रीक्वेंसी में गेन का वैल्यू 0 होना चाहिए और हाई फ्रीक्वेंसी करस्पॉन्ड कर रहा है जेड इज इक्वल टू -1. सो वी हैव टू हैव पोल्स at z tends to 1 and zeros at z tends to -1. Okay, in case of low pass filter. So you can see here I have written that poles for low pass filter, say for example z 0.9 पे है मतलब z नियर टू 1 है तो वो जो टर्म होगा डिनोमिनेटर में वो टर्म होगा z -0.9 फॉर एग्जाम्पल. और न्यूमिनेटर में क्या टर्म होगा? एक तो 0 है ऑलवेज z इज इक्वल टू 0, 0 में 0 ही होगा. ठीक है. और z का और एक वैल्यू होगा -1 पे. So that corresponds to zeros or numerator terms z plus 1. Okay. Similarly, so it is that same thing that is illustrated here in the book language. Okay. Now you see the diagram. That low pass filter, the top diagram is actually shows the locations of poles and zeros for low pass filter. लो पास फिल्टर में क्या हो सकता है, ये इस पोजीशन में है, देखो राइट साइड में, मतलब पॉइंट वन यूनिट सर्किल के नजदीक है, और कॉम्प्लेक्स कॉन्जुगेट भी हो सकता है, और यूनिट सर्किल के नजदीक है। ये सब पोल्स, मतलब पॉजिटिव वैल्यू है जेड का, ठीक है, जेड का पॉजिटिव वैल्यू that corresponds to low frequency at which the gain is high, and there are two zeros at z is equal to 0 origin and at z is equal to -1, ठीक है। ये हो गया लो पास फिल्टर। सिमिलरली फॉर हाई पास फिल्टर के लिए क्या होगा, इसका ऑपोजिट है, मतलब वो सब पोल्स एंड जीरोस हमको रिवर्स कर देना है, क्योंकि हाई फ्रीक्वेंसी लो फ्रीक्वेंसी पॉइंट्स है corresponds to z is equal to +1. Okay, z tends to +1, low frequency points. So low frequency points में हाई पास फिल्टर का गेन कम होना चाहिए, ठीक है। लो फ्रीक्वेंसी पॉइंट्स में हाई पास फिल्टर का गेन कम होना चाहिए, सो उसको जीरो में कन्वर्ट कर देना है, दैट शुड बी टर्म्ड एज, दैट शुड बी कंसीडर्ड एज जीरोस। एंड हाई पास फिल्टर में हाई फ्रीक्वेंसी में गेन ज्यादा होता है, सो हाई फ्रीक्वेंसी corresponds to values of z -1, सो उसको यू हैव टू कंसीडर एज पोल्स, क्योंकि पोल्स में गेन ज्यादा होता है, ठीक है। सो हाई पास फिल्टर में ये देखो नेगेटिव वैल्यूज ऑफ जेड, ठीक है, नेगेटिव वैल्यूज ऑफ जेड और -1, नियर अबाउट -1, ऑल द पोल्स एग्जिस्ट एंड जीरोस exist at +1, that is the reason. So you have so you all of you go through this part up to this slide. Okay, I will update this one in your files. So you just go through it up to this portion. So is it clear?
Yes, sir.
Okay. And also, have you downloaded all the class materials, previous class materials, so that I will remove from this one?
Sir, 1, 2, 3, 4 are downloaded. Sir. 5 I have downloaded.
Okay, 1, 2, 3, 4 downloaded.
Yes.
Okay. So I will remove. Okay, I will keep this for today. Okay, those who have not still downloaded. Okay, then I am stopping now.